Now that we've established the principle behind limits of functions of several variables, we're going to take a huge step forward and now talk about their derivatives, right? So we can find their domain. We understand about continuity, at least intuitively. Similarly for limits. Now the question is, what does it look like when we attempt to apply the process of differentiation to these functions of several variables? Well, it turns out that the process will be very similar to what we already know about differentiation. Let me just remind you something from a single variable calculus. So if f of x is differentiable, right, then we have, this limit definition for our derivative, right? So remember, that's our f prime notation, and it is the limit as h approaches 0 of this difference quotient, f of x plus h minus f of x all over h, right? And, initially, you might start out looking at the derivative as the slope of a tangent line or instantaneous rate of change. And it turns out, for functions of 2 or 3 or, more variables, there's a limit definition that looks very similar to this, and it has similar interpretations about slope and rates of change, right? But before we get into the interpretation, let's give the formal definition, right? If we have a function of 2 variables now, what does this look like? And then we will look at some methods of computation, right? So and let's just start with a function of 2. So let's just go from 1 to 2. So if z is equal to f of xy, then the first partial derivative, right? So this is what we're defining. Our first partial derivative of, you could say f or z, so you can use either this letter or just the generic letter f. So we'll just go ahead and say f of f with respect to x is, and this is how it's defined. So I'll give you one notation, and then later on we will discuss there's several other notations that can be used to represent this. So we'll use this one. We'll have our letter f. Now, instead of primes, you'll realize quite quickly that we kind of forego the usage of primes and we adopt other notation just because our functions are a little bit different, and the primes just don't give us enough information. So to indicate a first partial derivative of f with respect to x, we use our f, and then we put a little subscript for the x. And then let's write down how it's defined, right? In fact, it looks very, very similar. So in fact, let me write down the pieces. We are still going to have a limit as h approaches 0, right? We love those limits as h approaches 0. Now, this part of it is going to be replaced with f of xy. So let me put that there. So minus f of xy. So that part just translates over. Now, this part is a little different because here we had only one independent variable. Now we have 2. But if we specify that we're computing the partial derivative with respect to x, so this phrase is going to become even more important now that we're working with lots of variables. So if we're specifying that we're differentiating with respect to x, I will replace x with x plus h, and then I won't do anything with y. So this first term in this difference quotient in the numerator becomes f of x plus h comma y. And then we still divide by 0. I'm sorry, not divide by 0. We divide by h, right? And again, this is provided this limit exists, right? So provided limit exists. We always have to have that disclaimer, because what if our limit doesn't exist? Then we can't have in this case, a partial derivative, right, with respect to x. And then similarly, so let's just go ahead and define the two standard ones, basic ones, at least for first partial derivatives. So similarly, the first partial derivative of f, right, with respect to x. So in fact, let me go ahead and underline that whole thing, because it's really, yeah, that these are the things that we're defining. So the first partial derivative of f, but now with respect to y is, so again, what are we defining now? All of this. It's kind of a mouthful, but you get used to saying it, right? And as far as notation, we just change that subscript of an x to a y. So we have f sub y. We still have our limit as h approaches 0. And now this is where it changes. This doesn't change, the h in the denominator doesn't change, but because we are now doing a partial derivative with respect to y, I am not going to change the x variable, I'm going to change the y variable. So the first term in the numerator of our difference quotient looks like this: f of x, comma, y plus h, and then minus f of x, y, and then this is all over h. Again, provided the limit exists. It's always got to be in the fine print. All right. So right, this is what we have. We have these two key definitions, and they mimic the definitions from our previous work with calculus, right? But then those functions only had one independent variable. Now we have functions that have two. All right, so before we go any further, let's actually go through and take a fairly simple example and compute both of these, right? And see, just see how different or maybe how similar the process is to what we know about differentiation, right? And I'll take a fairly simple function. Let's use a polynomial, but this polynomial will have two independent variables, x and y. So let our z be, and in fact, let me use both notations. And then let's take something like 2x squared, and then plus 3xy, and then let's say minus y cubed, right? So again, not too difficult, right? Not too complicated a function. Let's go ahead and compute our f sub x. So let's compute our first partial derivative with respect to x, and we're going to use this limit definition. So it is the limit as h approaches 0. Now what does it say? Well, remember, when we're doing a partial derivative with respect to x, we don't change the y at all. So y just kind of, is off by itself. But then the first term in the difference quotient, in fact, let me go back up just so you can see it. It's right here. We're going to replace x with the quantity x plus h, right? So let's see what that looks like here. So we have 2, and then replace that x with x plus h squared, plus 3 times replace that x with x plus h, and then all the y's stay the same, so times y minus y cubed. So this is just the first term, right? So in fact, let me maybe put that in square brackets to really indicate that all of this that I just wrote in square brackets is this first term. So now I have to subtract my f of x, y, so my basic function, so 2x squared plus 3xy minus y cubed. and then this is all over h, right? So that's what the setup of this looks like, right? Well, now it's the algebra, right? So we have to, because if we plug h equals 0 in at this point, we're just going to get something indeterminate, right? So we're going to have to do some expansion and see what happens. Now, as far as the algebra, really, we just have to, expand this carefully and then multiply by 2. That's going to give us 2x squared. And then in the middle, we're going to have a 4xh term like that. And then for the h squared, again, when that's doubled, we will have plus 2h squared. And then everything else, basically I'm going to distribute the 3, distribute the y there. And this is what we have. So a plus, and then we have a 3xy, and then plus 3hy. And then we have a minus y cubed, so that's good. And then here, just distribute the negative to all 3 terms here. So minus 2x squared minus 3xy plus y cubed, and then this is all over h. Right? So yes, there are lots of terms, but really, it wasn't too bad. Right? And now let's see, now that everything's been expanded, let's see what are we going to be left with? Well, okay, so I have a 2x squared, and then I have a minus 2x squared, right? So those will go. I have a minus y cubed, right? So here, and then I have a plus y cube, right? And then I think that there's another term, a 3xy, and then a minus 3xy. So everything that's circled in red, it's gone, right? Like, magic. And so what are we left with? We really don't have that many terms left. I'm counting just 3 terms. So so what do we do? Well, at this point, because now if you look at the remaining terms, all the terms in the numerator, they have a factor of h, and there's also an h in the denominator. So if I were to try to plug 0 in, I would still get 0 over 0. So I'm going to factor the h out of the terms, the remaining terms in the numerator. That leaves 4x plus 2h plus 3y, right? And then what do we have left? And then we just have the h in the denominator. So then now I can reduce, right? So factor and reduce, and then I'm left with the limit as h approaches 0 of this quantity 4x plus 2h. I said 4, why did I write 3? So 4x plus 2h plus 3y. And when I evaluate this, now I can evaluate it by substituting 0 in for h, so that eliminates the middle term, and I'm left with something pretty simple, 4x plus 3y, right? So if this is and notice we have our equation of our surface in explicit form. We have our dependent variable z, and then we have our x and y here. So for this surface, right, its first partial derivative with respect to x is 4x plus y. So I'm just going to kind of highlight that, right? That's our f sub x. And if we kind of look at it, what happens? Well, when you look at the term that only had the x, it looks like just a regular derivative. It looks like a 4x, right? The term that has the y, the y cubed, it looks like that's just completely gone. But then this middle term that had both x and y, it looks like the x went away when I differentiated with respect to x, and then I'm left with 3y. Interesting. So, some terms completely go away. Some terms it seems like we differentiate it regularly, just a regular power rule right here. And then here, it's a little harder to see what's going on, but it again, remember we're doing a partial derivative with respect to x, and we have 3y. If I think about it this way, as 3yx, and again, remember we're not doing anything with y. Y didn't change at all, and it almost looks like when you differentiate 2x and you get 2, or 4x and you get 2. If we differentiate 3yx, and we end up getting 3y. So let's kind of keep that in mind. Let's compute the first partial with respect to y and see what that looks like, right? Because I'm feeling like there's a pattern here that we can exploit in a positive way, right? Exploitation doesn't always have to be negative. All right, so let's do our partial with respect to y. So similarly, let's set up our difference quotient, and when we're differentiating, when we're finding our first partial with respect to y, there is no change in the x, right? So in the first term in the numerator of our difference quotient will be f of x comma and then y plus h. So wherever there's a y, now I have to replace it with the quantity y plus h. So let's do that. So I'll use the square brackets so we can see it clearly. So 2x squared plus 3x, and now this y is going to be replaced with y plus h, and then minus this y cubed is going to be replaced with y plus h cubed, right? And then, right, so that's that one, and then minus f of xy. So this term right here is going to be exactly the same in this difference quotient. It's going to be 2x squared plus 3xy minus y cubed, and then all over h. So a very similar setup. The only thing that's different now is we're adding the h to the y term, or all the factors or all the terms that involve y. We replace y with y plus h. And then we have to do a similar thing here, right? We have to expand everything. And this one will take a little bit longer simply because we have a y cubed, but I'm going to make use of the binomial theorem, right? If you don't remember the binomial theorem, then you'll just have to FOIL it out, long ways. Or if you know the pattern for a perfect cube as opposed to a perfect square, which we had to use earlier, right? Again, I'm not going to have the algebra be a distraction. It's just a tool that we need. We want to focus more on this difference quotient and seeing what patterns emerge. So let's go ahead. Actually, in fact, I think I can... Well, yeah, let's keep the square brackets. That's fine. So we got 2x squared. Now distribute the 3x to the y and to the h. So we'll have 3xy plus 3xh. Now so there's going to be a minus. Let me write out the terms when you FOIL out y plus h. So you're going to end up having a y cubed, and then you're going to have a plus 3y squared h. Then you're going to have a 3yh squared, and then you're going to have an h cubed term, right? So again, if you need to, pause the video, FOIL out to your heart's content, like terms and all that good stuff, and this is what you'll get when you expand the quantity y plus h cubed, right? So there is the square bracket, a little bit more just because of the cube, but still not terribly difficult. And then distribute this negative to these three terms. So we have minus 2x squared minus 3xy, and then a plus y cubed. And again, this is all over h. That's a little longer difference quotient here, or term in the numerator. Now let's go ahead and drop all the parentheses, all the square brackets, and then see what if any terms will go away, right? So yeah, this plus sign looks too close to be a 7. Let me rewrite that. So there is the plus sign. So we're going to have 2x squared plus 3xy plus 3xh, and then distribute this negative, so all of these will become negative. So minus y cubed minus 3y squared h plus 3yh squared, not plus, minus, here it is again, all these terms are going to have a negative coefficient, and then a negative h cubed, and then just bring down these 3 remaining terms. So minus 2x squared minus 3xy, and then plus y cubed all over h. All right, so this is where we look to see what terms will go away. So I think we see this again, 2x squared and minus 2x squared. We have a y cubed right there, and then plus y cubed, right? So we have a minus y cubed plus y cubed. Oh, I skipped over this one. A plus 3xy, and then a minus 3xy. So again, several terms go away. So now it's starting to look a little less scary, right? So we have our limit as h approaches 0. And again, notice what's left. Every term that's left, all 4 terms have a factor of h. Well, let's do what we do with factors. We factor them out. So let's take out our h, and then we're left with 3x minus 3y squared, and then minus 3y, and then minus h squared. Right? So that's what we're left with. And then this is all over h. And now we really start to see the light at the end of the tunnel. And we know it's not an oncoming train. So we can reduce this. And we have the limit as not x, but h approaches 0. We have the quantity 3x minus 3y squared minus 3y minus h squared. And then when I put, when I replace, all right, I think, I'm missing an h here. Yeah, so this one has an h squared, and we factored out an h. So there's supposed to be an h there, and let me just fix this one. There we go. We have to keep track of all these h's. They're very important, right? Without them, this process falls apart. So there we go. And then when we evaluate this at as h approaches 0, these 2 terms go away, and we're left with, again, something not terribly complicated. 3x minus 3y squared. Right, so this is our first partial derivative of that function with respect to y. Right, so let's just kind of summarize. So that we have everything, let's say, in one line. So remember the function that we started with. It's the 2x squared plus 3xy minus y cubed. Right. And we came up with these 2 things. When we did the first partial derivative with respect to x, you remember what we got? We got the 4x plus 3y. And then now we computed the first partial derivative with respect to y, and we got this, 3x minus 3y squared. And then we look at that and say, okay, there's too much similarity with what we know about derivatives for us maybe to now start thinking, could I replace my limit process with just my standard rules with a slight tweak, right? Can we do that? Well, let's again look closely here. And let me write the function in two ways. Basically, just switching the factors x and y here. So I'm going to keep the 2x squared, and then I'm going to write this as 3y x, and then I'll have my minus y cubed. So again, let's look at it. When we differentiate it with respect to x, it looks like this is just a basic power rule. The 2 comes down, multiply the 2, and we get 4x, and we subtract 1. And then the middle term, because we are differentiating with respect to x, and remember, we didn't change the y at all, right? We didn't add any h's to the y. It's almost like the y is treated as a constant. So I have this constant, quote unquote, constant. You can't see my air quotes. I don't know why I just did air quotes and you can't see them. But anyway, I told you about them, so now you know they exist. So you have this 3y times x. Well, if I think of what's in parentheses as a constant, then I know that when I differentiate a constant with respect to x, I just get the constant back. So that kind of justifies this term. So what about the y cubed? Well, again, if I am treating y as a constant, then this whole thing is a constant. There is no x at all in this term. So again, now we know that when you differentiate constants, you get a 0. So maybe that explains why there is no, additional term here. Let's see if that, that intuition, does that also kind of justify what we ended up when we did our partial derivative, first partial derivative with respect to y. Now, this term doesn't have any y's at all. So remember, when we were doing our f sub y limit calculation, we didn't change the x at all. So if we're treating x as a constant, then this whole term is a constant. And we know differentiating a constant will give me 0. So that kind of explains why this just kind of vanishes, right? The middle term now, if I'm differentiating with respect to y, then it's like this whole 3x is like a constant times y. And I know, based on my power rule, that when I differentiate, let's say, with respect to y, if I have a constant times y, I'm just going to be left with the constant. And that's why, at least that explains why I'm left with a 3x here. And then when I look at this term, when I differentiate with respect to y, yeah, I get my regular power rule. You bring down the 3, subtract 1, there you go. So it appears, and it's not just now an appearance, it is in fact the truth, that when differentiating with respect to x, we treat y as a constant, and we use our standard rules for differentiation, right? So here is kind of these are some rules of thumb. That's a thing, right? So 1, when finding this partial derivative, what we do is we hold y constant. So hold y constant, and then we differentiate, quote unquote, there's my air quotes again, normally with respect to x. So hold y constant, differentiate with respect to x. So we get to use all our rules, right? But now we just have this extra thing in terms of what we have to do with y. And similarly, f sub y, as you might expect, we're going to hold x constant, right? And then differentiate regularly, right, with respect to y. And that's how we don't have to reinvent the wheel as far as our rules. Those rules will still apply, which is good. It's just we're applying them in a slightly more, not even complicated, but just, more involved, maybe you could say more sophisticated context, right? So let's see if we can do an example now using this, and then we'll just sort of wrap up this video and do lots more in the subsequent videos, right? And then also introduce some other notation. Let's end with an example here. So instead of just using a polynomial, polynomials are good because the difference quotient calculation isn't too difficult. It's easy to see the pattern, but then once you understand that pattern, then we can apply it to more complicated functions. So I won't make this one too complicated, but let's say here is the equation of our surface, if you will. So let's say we have x squared times the sine of y, and then plus the square root of y times e to the negative x. So let's say it looks like this. Right, so it has some familiar functions that we know how to differentiate. Let's see if we can apply these rules of thumb and find our first partial with respect to x, first partial with respect to y. So let's do our f sub x first. So again, what we're going to do, and for this calculation, the sine of y and the square root of y are going to be held constant, right? So for f sub x, we're going to treat the sine of y, right, and the square root of y are treated as constants. I'll put that in quotes because they're not true constants. Obviously, they have a variable, but for the purpose of computing this partial derivative, we're going to pretend that they are. So we get to play make-believe, right? So if this is a constant, then it's a constant times x squared. So when I differentiate this term with respect to x, that constant will come down, and I will apply my power rule to the x squared term. So it looks like this, 2x. And since it's a multiple, then you just bring it down, the sine of y. And then we have term by term properties, right? So we just differentiated that term, then we're going to bring our plus sign down, differentiate this term. But again, because the square root of y is being treated as a constant, it comes down, so it's root y, and then times, now the derivative of e to the negative x with respect to x is negative e to the negative x. So kind of putting this all together, not much in terms of simplifying we can do, but we will have 2x times the sine of y, and then I'll just take this negative and put it in front, so I have minus the root of e to the negative x. All right, there we go. So let's see what it looks like. How is it different when we're computing f sub y? Well, in that case, everything that has an x will be treated as constant. So we're going to treat the x squared and the e to the negative x as constants, right? Just for this purpose. It's like, even though these are two independent variables, it's almost like we're keeping one of them fixed, and then we're letting the other one actually vary, right? So f sub y. So if the x squared is a constant times, so that constant multiple comes down, and then I multiply by the derivative of the sine of y with respect to y. Well, that's cosine of y. Plus, now for the square root of y, then we think of that as y to the 1/2, and then we do our familiar, power rule, and when you rewrite it, you're going to end up getting 1/2 root y. That's the derivative of the square root of y, and then the e to the negative x is brought down, again, because we're treating it as a constant. So e to the negative x. So when we put this all together, here is the partial derivative of this function with respect to y. So it's x squared cosine of y, and then I'll write this as a single fraction. This is e to the negative x over 2 root y. Right? So we did a lot in this video, right? We first did these limit definitions, and then we've now established a way to use all the rules that we know, right, in the context of these functions of several variables. So, let's give ourselves a pat on the back, but not too hard of a pat, because we have a lot more left to do. So there's always stuff to do. And I guess we should just go do it. So I'm gonna hop on over to another video. Hopefully you'll join me. See you then.